All right, let's get started. Welcome to the session on concurrent programming in C++. We're going to talk about some of the multi-threading facilities available in C++. I have to say that I was quite pleasantly surprised at the facilities available because I think they've done a fairly good job in terms of bringing up to speed several things that we have learned from a lot of other languages, and C++ has done a fairly good job. What are some of the issues, though? Well, the first problem is concurrent programming is really hard. It is not something that we can do so easily. A lot of times when we write code with single thread, the code is fairly easy to understand, easy to maintain. People come to work, they smile at each other in the mornings, and then you decide to use multi-threading, and the code turns into a monster. And nobody ever smiles at each other after that. And then we start debugging endlessly. We have to be very careful using some of those techniques, but one other problem that used to be traditional in C++ is C++ always touted portability. When it came to multi-threading, though, that was not really the case in the past. Thankfully, the new libraries actually bring back portability quite a bit, so that's one of the other things they've done really well. Let's take a look at some of the things they have done in terms of the library itself. The first and foremost is platform neutrality. You can pretty much take this code, they'll map it over, and you can run this across different machines, which is a really good thing. Well, one of the very first things to consider is how many threads are advised on your system. So that's basically called as hardware concurrency. Well, let's take a look at this really quickly. Hardware concurrency, what does that really mean? So pretty much, I'm going to output right here, standard, let's say, thread, and then I'm going to ask for the hardware, and then I'm going to say concurrency. And in this case, of course, I'm going to ask for that number on my machine. It tells me it's 8. It's a lie. I don't have 8 cores on my machine. I have 4 cores on my machine, but it still wants to generously tell me that I have 8. That's because it's using hyperthreading. But the first question to ask is, why? Why bother? What's the big deal? I think this is important for us to know as developers, because we can get pretty overzealous and say, hey, I can create as many threads as I want to. So let's say you have a fairly big problem and you decide to say, I got all these values in front of me, I'm going to throw threads on them. You could pretty much write the program in a way, and I've done this, where your parallel code can and will run a lot slower than your sequential code. That's not the intention of using parallel programming, isn't it? So what does this really mean? Why should we really care about? And that's what I want to really talk about in the beginning, because we can be very naive about it. So the question is, how many threads should you use? Not how many threads can you create. You can create as many threads as the amount of memory is available and the system will allow you to do. How many threads should you create? Well, the answer to that question heavily depends on a few factors. If you are programming computation intensive, what that means is my code is number crunching. I am going to get data and do a lot of computations on it. I'm working for a client right now, and what we do for them is we got about 60 million pieces of data that we have to process. And the minute you touch one piece of data, that produces 15 million babies to process. And you can imagine, we're going to number crunch these through a series of math equations. On one day, I just clocked and found out how many computations I was running when I called one function. And that resulted in 53 billion computations. And it's a very nerve-wracking work because thankfully, the clients are extremely nice people. Otherwise, I wouldn't be working there. They would come to me and say, how are things going? And I would say, I worked so hard the entire day. I made things faster by 2 seconds. And they would pat me in the back and say, good job. Now make it faster and go away. And this is really number crunching work. We got to be very careful how many threads we throw on it. If it's computation intensive, your threads are going to be busy doing work. And the least thing you want to do is to take a thread which is busy doing the work, rather the CPU that's busy doing the work, and say, get off so I can put another job on the CPU. So in that case, the number of threads you should maximum have is less than or equal to the number of cores. That's why this number is extremely important. On the other hand, if you're using an IO-intensive operation, you could go 1 minus the blocking factor, where the blocking factor is the amount of time a task is going to spend time being blocked. So if you have an I/O task, for a computation-intensive task, the blocking factor is 0, which is, number of cores divided by 1 minus 0 is 1. Number of cores is the number of threads maximum. On the other hand, if you're I/O intensive, if I'm sleeping half the time, it's going to be number of cores divided by 1 minus 0.5, which means you could potentially give me twice the number of cores as the number of threads. In fact, if I'm sleeping 90% of the time, you can give me 10 times more core than the number of threads as the number of cores available. What this really means is, just because you can create a lot of threads doesn't mean you should. You should be very careful about how many threads you create. And when you exceed this limit, your performance actually goes down drastically. You got to be very careful about it. And that's one of the reasons why this number is pretty critical for you to know. So when you start your process, you want to ask, how many threads can I really use on that given hardware? And depending on your particular hardware, you need to decide what that real number is. At work, the machines I'm using have literally hundreds and hundreds of cores on them, so I can configure them to go a lot more than obviously on my little box right here. So given that, how do we really start and use the threads? Well, that's easy one to do. You can take a particular function and delegate that to a thread right off the bat very easily. So for example, let's say I have a function called print info right here, and this is going to simply, it doesn't really take any arguments right now, and all I'm going to do is output, let's say, info, and then in this case, let's say standard, and then I'm going to ask for the thread, and I'll ask for the get ID of the thread, and then I will ask it to be printed out, and then maybe end it. So this is going to print me the thread information, but how do I really delegate to this particular thread? Well, that's the easy part also. I can simply say thread. I can create a thread right off the bat and schedule the print info to execute in that particular thread. So you pretty much create a thread object, really easy, not very difficult at all. So you basically create the thread object. You can even send a little data to that method if you're really interested. In this case, I'm not sending any, but that's perfectly fine. You can start it. But one of the things you need to really do after this is you're going to call a join, and you're going to ask the thread to really wait for, the main thread to wait for that other thread to complete at this point, so you can actually wait and report on that result when it comes out. So obviously in this case, that's get underscore ID on the current thread, not the thread itself. So I'm going to say this underscore thread. So this is going to be information about the current thread or whatever the thread ID is. Well, that was not too hard. We got the ID of the thread. Depending on the machine you are running, it's going to be different. I'm running on the Mac right now. This particular slide I created, I think, on Windows, so you can see the numbers are fairly different. So you can see that it's going to be some value being reported. On the other hand, I'm going to create a thread 1, let's say. I'm going to create a thread 2 right here, so I can create multiple threads. And then, of course, I can ask it to wait for thread 1. I can also ask it to wait for thread 2 to be done, and I can run this and see what the result is. And that also illustrates one small issue that you may run into. Notice that in this case, I have them printed and I have an end-L, but these kind of jumbled up. This couldn't have been easier for me because I wanted to show you this problem. Usually it doesn't happen so easily. Today is my lucky day, and you can see the output really messed up. That's one of the things we have to be very careful about, how these things are going to appear. So when I run this code, the result may actually vary depending on what you do. So I'm just running this here, and you can see that it's quite jumbled up when it comes to the output, even though I have an end-L in there. Well, what do we do about when things collide like this? We'll come to that in just a minute. So you create a thread very easily by simply using the thread object. And this brings the question, we got to know what really is happening. There are two distinct things that you need to keep in your mind. There is the thread of execution, and there is the thread object. And it's important to keep these two things in mind very clearly, because our human mind is very good at getting confused between the two. The thread of execution is going to happen at the system level. You have no control over it most of the time. The thread object is a pure abstraction. A thread object is an object that allows you to get information about this thread of execution and to maybe monitor this execution. And you need to keep these two things in mind. And when you create a thread object, the thread of execution starts running, and the thread object is attached to that particular thread of execution. When you say join, your thread object is going to block your calling thread until the thread of execution actually finishes. If you don't care about it, you could detach and say, let the thread of execution go on its own, known, I am not interested in monitoring it anymore. You can detach yourselves, and at that point, the thread object will be completely unattached to the thread of execution. It no longer monitors the thread of execution. So keep those two things in mind, the thread object versus the thread of execution itself. So we created a thread really easily. How else can we create a thread? Well, in this example, I just passed a function to the thread to create it. But there are two other options available to you as well. One of them is you could actually create, I'll come back to this in just a few minutes. You can also create an object. Like in this case, I have a class called sample, as you can see. And all that the sample contains is an operator overloaded parenthesis. And once you overload the operator overloaded method parenthesis, you can actually pass an object of that type to the thread, and it would then call that particular method. That's another easy way to do it. A third way, which is my favorite way, is you can pass a lambda expression as well. So here is an example of passing a lambda expression where you can just simply say, I want to pass this lambda called, well, of course, lambdas are anonymous methods. And here's a lambda I'm passing to thread 1, and this lambda will be executed as soon as you kickstart this particular thread. So there are these three options. You can send a function, you can send an object that has an operator overloaded parenthesis, and then you can also pass a lambda expression as well as the three different things that you want to send to the thread. But obviously, in this example we just saw, there is one small problem, as we saw, that the output is kind of messed up and jumbled up. What can we do about it? Well, what we are doing here is something called evil programming. And that is, we are using a shared resource from multiple different threads. And that usually doesn't go really well. So what do we do about it? Well, one solution for that is to provide a mutex that you can provide in here. So you could create, for example, for instance, a mutex right here called, let's say, cout mutex, or whatever you want to call it as. And then I create a mutex. And then what I can do here is, I can simply say that the cout mutex, I can say lock on that mutex. And then when I'm done with it, I could say, in this case, unlock and release the lock on it. So you're saying when multiple threads come in, let the threads fight over each other. It is kind of like the bathroom door, right? You may have multiple people using the same house, but you have one bathroom. It's good idea to lock the door when you go in, and then as a result, of course, you can be the only person using the bathroom, which I think is a nice thing to do. But of course, if you have teenagers at your house, they go in but they never come out, and that can be kind of annoying. That's exactly the problem with this. There's no guarantee of unlocking, and you bang on the door and say, get out of there, you've been too long. Well, how do you deal with it? We'll talk about that in just a few minutes. So the whole idea here is to lock and unlock so that you can be mindful of this resource, and you can see how nicely now they are on two different lines rather than being jumbled up on one line because they kind of synchronized and one used and the other used. No guarantees which one actually used it, but of course one goes in, the other comes out, then the other one can go in. So that is an example of how you can use a mutex to resolve conflict between threads as well. We'll talk more about this a little bit later. Well, so think of this abstraction I talked about, separation of the thread and from the thread of execution from the thread object itself, and you want to be mindful of this. Talking about which, notice in this example I have two threads I have created. This is more of a feature in C++, which I'm really not sure if I like or don't like. I'm still kind of thinking about it. I have a thread running on that, still thinking. But in this case, when I run this code, notice it is giving you an error right there. It says terminating blah, blah, blah. What it is telling you is that you created threads, but you never really bothered to join them, and that's what it's complaining about. So if you don't join a particular thread, you get an error, but when I do join the threads, you can see that I don't get any errors at all. So in a way, you could argue this is a nice thing. You get an error if you were forgetfully not joining a thread. What if I don't care to join a thread? What if I don't really have a reason to wait for it? Then do a detach instead of a join, and that's perfectly fine as well. And you could do a detaching of the thread. But of course, when you do detach a thread, when I run this, you didn't see any output at all. So what in the world is happening? Well, detach means you have just created what's called a daemon thread. So what is a daemon thread? A daemon thread is a thread that does not hold hold the main thread hostage. So if a non-daemon thread usually will require the main to be running and the program to be running when those threads are alive. A daemon thread says if the main quits and all the non-daemon threads quit, a daemon thread will never hold your program running. So if you detach a thread, you are simply saying, I don't care about you. You can just keep running. I'm going to shut down and go home. And that's basically what a daemon thread is. So it's kind of like you tell a staff saying that, wait in this room and turn off the light when there is nobody in the room. Obviously, you don't want the staff to say, I am here, so I'm going to keep the light open. Usually it means nobody other than you are in the room. That's kind of the difference between a daemon thread versus a non-daemon thread. A non-daemon thread will keep the application running. A daemon thread will not. Well, detach is a way for you to create non-daemon threads saying, hey, I don't care if you're running or not. So we can join, we can detach. Either one is fine. And we saw how to detach as well. That was not really hard at all. But of course, you can ask if a thread is joinable. So there are two things. If a thread has been, you have not done anything to a thread other than create it, it is joinable. If you join a thread, then it is no longer joinable because you already joined it. If you detach from a thread, even though the thread of execution is running, the thread object is no longer joinable because you have detached from it. So that is something for you to keep in mind, if you will. So you can go ahead and ask the question, output right here, thread 1 dot joinable. You can say joinable, and then you can ask that question whether this is joinable. And in this case, it tells you 1 right there, which means it is joinable. On the other hand, after I call the detach, if I ask for exactly the same question, you notice it's a 0 right there because it's been detached and it's no longer joinable. So that's a way for you to know whether you have the ability to join a thread or not. You may have a thread object with you by mistake, but it is detached already from the thread of execution, meaning don't mess with it anymore. It's pretty pointless to be using at this point. So we talked about joining. But there's one other problem though. What if there is an exception in the code? You always have to worry about exceptions, isn't it? So what if the code blows up? If you have a join and if you have an exception, your join is not going to be called. In that case, of course, your program is going to give you an error because you neither joined nor detached. What do you do? Well, you could try to put a try and catch, and within a catch block, you could put a join. Outside the catch, you can put a join, but that code becomes really, really messy, and you kind of scratch your head and say, gosh, the code really becomes ugly. How do I manage this? So here's what you don't want to be doing. Putting a join here and putting a join over here, that can become really, really messy. So one way to solve this particular problem, to avoid these verbosity and error-prone code, is to use the so-called RAII pattern, which is the resource acquisition is resource initialization pattern. So what I'm doing here is I'm creating my own thread class, as you can see. So this thread class internally is going to create a thread, but I use an enum called join or detach just to make my life easier. You can tell me what your intention is, whether to join the thread or to detach from it. But then the beauty of this one is that in the destructor, I am going to either call the join or I'm going to call the detach. And of course, if there was an exception, this object will still be destroyed. And as a result, either a join or a detach will happen. I don't have to worry about it later on in the code. So you can wrap your thread into this object. Then you don't have to worry about calling detach. You don't have to worry about calling join. You let this object deal with it by specifying. How would this look like? Well, the way you would use this is as follows. You would say a thread. Notice this thread now is our own class, not the std : thread, which then wraps the thread as part of it and then manages the depth of that particular object. If exception were thrown, this is going to take care of it. So you can pretty much wrap your resource around it and deal with it properly. And of course, there are a few things you got to be very careful about. How do you pass your object to this particular thread? So in this example, I have something called Sam, and I'm trying to pass Sam to this thread. This is also known as a bad idea because it's going to try to make a copy of it, and I incremented Sam's age, but it's an old age. So what are you going to do do instead, what you want to do is to use a reference. So you can send a wrapper reference rather than sending the object itself by reference, and that way you are really passing the object reference properly. So little things like that, you got to be very careful to pass it around, but that's nothing new for us. You've done this in C++. It always surprises you when you don't expect it. So that you got to be very careful about how you pass these objects around. Now, having said that, starting a thread is the easiest thing. But then the fun begins. Normally what happens is when you start running multiple threads, you always want to communicate between different threads. So what is the worst way to communicate? The worst way to communicate is using what is called a shared mutability. Now think about this for a minute. Mutability is extremely common in C++. We mutate stuff every corner we turn. And a lot of times we do this because it's a lot performant. And so mutability is okay. What about sharing? Well, sharing is a good thing. Remember what mom told us. We should really share. That's a good habit. So mutability is okay. Sharing is really good. But shared mutability is devil's work. And the minute you bring in shared mutability, all kinds of problems come to life. And this is when it becomes really, really, really sad the way we work. So shared mutability is purely evil. We should try to avoid this as much as we can. But of course, there are times when we do want to program with shared mutability. Like I mentioned, especially for performance reasons, we often do this. So it's a risk you are taking quite a bit. So how do you really deal with this? Well, you have to properly protect your data to do this. So there are some rules we have to be very careful about. Race conditions are something you want to avoid absolutely. When multiple threads run over each other, the result becomes absolutely unpredictable. And these kinds of errors are extremely hard to track, as you know. So you have an error in your code, you run it, it gives you a wrong result. You are scratching your head, you call your colleague and say, look, the code did not work, it gave me a wrong result. After looking at this for 30 minutes, your colleague then says, run it again. And now the result is completely different, right? It can be very annoying because it's very unpredictable. You cannot just rerun it to see what the result is. So what do you do about it? You got to thoroughly examine the code to make sure that it is really correct from the concurrency point of view. So here's an example. I have a variable called aCount, and within this change method, I'm making a copy of the aCount, incrementing the copy by that amount, and then setting the value back in. Now, this is completely unprotected code, inviting problems. Then in this, I created 20,000 threads, and then I pushed through the thread the change function, but I ask it either to increment by 1 or to decrement by 1. Now, if it is even and odd, well, it's 20,000 values. We know that there is as many even numbers in 20,000 as there are odd numbers. So what should the result be when I'm done with this? The result obviously should be a value of 0 because I incremented as many times as decremented as many times. But when you run this program, you can absolutely not predict what the result is going to be. It can be a really good program to generate lotto numbers if you want to. Pretty random every time you run it, isn't it? Because it's not really clear how the threads are going to run, and why is that? The reason is two threads may come in and read exactly the same value, and they're competing against changing the value. The last one is actually going to win. The way to think about this is that you have multiple people trying to put their hands on a bowl. It's going to have things spilled over. That's exactly what's happening in this case, right? Not very, very much fun. So what do you do about this? Well, one way to decide this is to use a mutex, and then you can call a lock on this and you can call an unlock on it, just like I did a few minutes ago with that other example. The good news about this code is now the result will be absolutely predictable almost, unless there was an exception someplace. What if this code in the middle of lock and unlock blew up with some exception? Well, then you're going to have an unpleasant live lock. Live lock is different from deadlock. Live lock is where you wait forever for an event that will never ever happen, right? This is like you have a teenager at home who went to the bathroom but slipped away through one of the windows. You don't even know that they're not in the bathroom anymore, right? Like teenagers do. You're going to wait for a very long time for them to come out. I know those of you laughing did this when they were teenagers. That's why they're getting much laughter about this. So the point really in this case is that's a live lock. You're going to wait for something to happen that will never ever happen. So as a result, what do we do about it? Well, here's a way you can actually, and this is the part I really am happy for in C++, because a lot of languages don't do this. A lot of languages will come to this point, and then they will give you one solution which can be summarized into 2 words called good luck. And C++ said, okay, we'll be kind to you, we'll give you a bit more solution, and they give you what's called a lock guard. I really like a lock guard. What is lock guard? It is the RAII applied on locking itself, and I do have to admit, they have done a really good job. The day I learned about this, I said, I really love these guys. They've done a good job on this. So what does a lock guard do? Lock guard, as you can see, wraps the mutex and gives you the lock on it. You never unlock it. When you leave the scope, the unlock happens automatically. Whether normally or through exceptions, you're perfectly safe to handle at this point. That's exactly what this is giving. Now, of course, in programming, you know one thing. When you solve one problem, it gives rise to another problem. So I'll talk about what the other problem is in a few minutes. So this at least solves the current problem we have at hand. We'll talk about the other problem in just a few minutes. So in this case, of course, we can use a lock guard, which is really good. Moral of the story, don't ever lock and unlock mutex. That's a bad programming. Always use a lock guard use that rule until I change it in a few minutes. So don't ever use lock and unlock. That's bad programming. Okay, so we talked about this, but it's not a panacea. We got to still be careful about how we use this. You can still get into trouble by not protecting things properly. There are places where you could really get into mess with this also. How do you prevent this? Well, first of all, make sure your data never escapes. So let's talk about what this means. Let's say I have an object with me. You lock, you call a method on me. I give you a reference to an object, maybe an internal state, and then we unlock it. Well, after the unlock is over, you come and change the reference, I'm in trouble again. That is called escaping the object. So when you do concurrent programming, you have to make sure that your data never escapes from you. So where we return references, we have to be very careful, because it's possible that you have just given out a reference that somebody could come and change it afterwards when the lock is no longer being held. So things can still go wrong. The next problem to think about is deadlock. So what is deadlock? Deadlock is, of course, where multiple threads are waiting on each other. One of my favorite analogies to use is you have a boy and a girl at home. The boy grabs the sugar and waits for the milk, and the girl grabs the milk and waits for the sugar. What is this called? It's called parenting nightmare. And this is when they both are going to wait on each other and not have breakfast. So what do? You make a rule. You should not get sugar anymore until you have gotten the milk already. And that's exactly the whole point about. One way to avoid deadlock is to make sure that you always acquire the lock in one certain order. Now, the good news is you acquire the locks in one certain order. The bad news is I have no clue how to get the locks in one certain order, because it's not like you have a very good plan where you can take these objects and put them into order. And anytime we do coding, what happens? This is one thing I've learned over the time. You let a programmer write code, that becomes a liability, right? This is the time and again. The more code you write, the more bugs you have to maintain. So if this is something that's got to be done the right way, you want to give it to the adults who can write it the right way. I'm saying it sincerely, because when I am working on my application, I have a lot of stuff on my mind already. That's my focus. Don't tell me to focus on my app and focus on infrastructure issues and library issues. This is the reason I use libraries, so I don't have to depend on those things myself, and I can take somebody who has done a good job and use their solution. So if deadlock should be avoided, why don't you guys do the work to avoid deadlock, then tell me, lock them in the right order. That's another thing they've done really well, and I really am happy what they have done. So let's see what the answer is. Notice there's an account here, and the transfer from locks guard 1 and then it locks guard 2, this is also known as a bad idea. Never acquire the lock more than once in your execution sequence. So in other words, you should never acquire one lock, and while you hold on to one lock, you request for the second lock. That's a really bad idea, right? Because the lock you're holding and then you're requesting for another lock could cause the deadlock, because somebody else may be holding that other lock and waiting for the lock you already hold, and now you're in tension back and forth holding on to this. So this is a bad code. Don't write this. Don't get one lock and then wait on the other lock. So what do you do to prevent this problem? Well, what you can do nicely instead of doing that is you can now use the lock again, but in this case, notice this is not a lock on the mutex, but a lock function directly. That lock function takes a sequence of locks, as you can see right there. And in this case, of course, it gets those locks, but unlike you and I calling the locks, it is going to acquire the locks in the order properly internally, so you don't have to worry about it. So always acquire the locks in one shot, never acquire one lock and request for another. And then, of course, you're asking for a guard lock 1, and then you can slowly ask for the guard lock 2. That's perfectly fine. And it will guarantee that it acquires the lock in the proper order for you, and then you can go back and use it. So that way you can prevent the problem. And what does this guard lock 1 and guard lock 2 do? Well, they are really for unlocking purpose. So you don't worry about, oh my God, I forgot to unlock it. It'll take care of the unlocking properly. This will take care of the locking in the proper order for you, and you can prevent deadlocks by doing this. So this is a really good way to handle it. So you can do a lock, and then you can do a guarded lock for unlocking purposes. When you're done with it, that'll be very safe. So never acquire multiple locks on one at a time. Always acquire the locks in one shot, and never lock on an object you already locked already. That's not a good idea. And avoid nested locks as well. So given this, there are times when you want to acquire a lock, but unfortunately though, you want to make sure that you are, say, how do I make sure I don't get a lock I already have gotten? This is kind of stupid, right? It's like you have a lock, but then you lock yourselves out by asking for a lock again. I don't think there is any better way to feel stupid at the end of the day, because you're debugging this for a long time and you realize the lock is being held by you yourself, which can be very vexing. So one way to prevent that is to use what is called a unique lock. When you use a unique lock, it knows that you already have a lock, so it grants you the second time you ask for it rather than blocking you out. So that could be a really nice way to solve that one bit problem, is you could do this. Another advantage of this is you can also do what is called a deferred mode. So you can just say you can have a dibs on this, but you don't want to lock it until a later time. You could do that as well. So you could use a unique lock, and that's another thing available already. You can say unique lock right there, and then provide the lock that you want to use, and you can say instantaneous or deferred, and then of course you can then come back and use it later on when you really need it. So you can start defining these kinds of locks. Another, of course, you want to also avoid race conditions that may arise in this form also. This is more related to leaking the object like I talked about earlier, so make sure you don't leak your resources, make sure you hold on to the locks properly. So how do you deal with that? One way to deal with that is to maybe provide a method explicitly to acquire a lock on your object. So here's the problem, right? If my function is going to do locking internally, and say that I have two functions. You call my first function, it locks and then does its works and unlocks. Then you call the second function, it locks and does its works and unlock. But the problem is, when you call these two functions, between these two calls, that very small moment when you release a lock, somebody could get in, and that could lead to problems. So what you want to do is to do a lock around those two methods entirely, not individual methods separately, and that's when you could really get a function to give you a lock, and then you can take your time to call multiple functions, and then you can come back and unlock it when you are done with it. Again, you have to think multiple times about how this works. So that's what I'm going to do in this example, is to make sure that I acquire the lock outside of this. Notice that I get lock, so I can call the get lock method, and then I can do my work, and when I'm done with it, I will release the lock on the object. That way I can call multiple methods without fear of somebody intruding between my calls. So there is another problem, though, that we have to deal with. And that is, let's take an example of a little example of a singleton. You know, what is singleton? Singleton is the easiest pattern to read about and the most difficult pattern to implement. Because if you go search on the web, implement singleton pattern, you'll be surprised that people have 7 solutions, and at the end of the 7th solution, they say this doesn't still work. And this is really hard to get correct from the concurrency point of view, and can be very vexing. Well, here's an example where in the singleton, you can see that I have a get instance. This checks if the pointer is null. If it is null, it acquires the lock, and then again checks if it's null. It's still null, because between the time you checked and the time you got the lock, somebody could sneak in and change that too. This is really sad programming, isn't it? Well, how do I avoid these problems? It would be nice if somebody can do this for us. That's exactly what call once is. So call once is a method that will say, call this only if this has not been called already. So when multiple threads compete, one thread will do this work, all the other threads will say, oh, this has been already done, and they can skip over. So in other words, you take all the silly code we do and you move it under a library so that can be done for us, so we don't have to duplicate our effort doing it over and over and over, and that's exactly what the call once is doing. For this to work, of course, you have a pointer once, or whatever name you call it, and you pass that over here, so they compete on that reference, and then they decide whether to call that method or not call. This removes the burden of writing all that silly code and wondering if it's still correct, and that takes care of that. So call once is a good idea. Well, similarly to synchronize, you can use variables to synchronize as well, and these are conditional variables you can synchronize. So this is where you have a signal and wait, so you can say notify once, and then you can wait on that. So if you have 2 producer and consumers running, and you want one to produce a result and you want the other to wait for it, how do you signal between those 2 threads? That's basically what conditional variables are for. So you can create a conditional variable, share between those 2 threads, when the thread that produces the result can do a notify, and then the thread that's waiting on the result can do a wait on it, and then continue doing whatever work it needs to do after that. That can be a very powerful way to communicate between those 2. One other suggestion before we go any further, the rule of multi-threading. And I would say this is a rule not only of multi-threading, this is a rule of life and multi-threading. Never do anything without a timeout. It is kind of like finding that perfect love. The sensible person will look for a perfect love and then eventually time out. Otherwise, you get old and die alone. That's exactly the rule of life and programming also. You never do anything without a proper timeout. You say, I want a lock, but I'm going to time out if I don't get it after a reasonable amount of time. You can prevent deadlocks as well. So everything you do in concurrency, always do with a timeout, never do without timeouts. Okay, so let's stop right there. We have done this, and what is one of the biggest really problem we see so far? The problem so far is, we can summarize it this way. Hey, great, I have a beautiful way to create threads. I can run these threads concurrently. I'm happy for that. That's awesome. But one big hole, I cannot deal with mutability. I don't want to create a global shared variable and have all these threads work on it. That's really a poor programming practice. There's got to be a better way to communicate between these threads. How can I do that? So take the multi-threading, the thread creation aspect, and mix it with the communication aspect to exchange data. So you don't want, it's kind of like this glass over here. You don't want to put this glass here and say, you and I are going to share this. That's not a good idea. Well, I'm going to fill the water, and then I'm going to give it to you with a full glass of water, and you can now take it and move on. That way you know the glass is full when you get it. Otherwise, you're going to keep checking, did Venkat fill it? Did Venkat fill it? There's no reason to do that. So how do I really send you an object? That's exactly where future comes in. Future is a really nice implementation where, think of a future as an object that goes from one thread to another with the data that is being carried over. So here's an example. Fibonacci is computing the Fibonacci. As you know, this implementation can take a really long time if the Fibonacci number is big. So print result wants to print the result of Fibonacci when it's done. But notice the signature of print result. It is not a long, it's a future long. So this says, when you give me a future, I'll call a get on it, and I will wait on the get, and then when the get gives me the result, I will print it. So this future long is what I'm going to print, but how do I get that future? Hey, look at that thread like we did before. So I'm going to call the thread, and I'm going to send the print result to the thread. But notice I'm sending an async object right now. An async will run in a completely different thread, but the result of async is actually a future. So what are we avoiding? We're avoiding the stupid global variables. You don't want two threads to go at a variable and do mutex to control that. Instead, you say, hey, you thread, you go run, do your work. When you're done with your work, you send me your result through your future. I will wait here on the future, and when the result arrives, I'll move forward, and that becomes a nice way. I call this civilized multi-threading, right? The other one is called barbaric multi-threading, where you put a global variable and you attack each other on it. This one is a very civilized. You go do your work, I'll wait here. When you're done, you send me the result, I'll carry on after that. That's exactly what this future is doing. So in this case, of course, this will run, get the data, and the future.get will be blocked, and that will trigger off and run when the data becomes available. So, but there is one problem though. You are starting an async, but remember we are sensitive to threads. You don't want to be creating too many threads. What if the thread that's creating this code doesn't have any real work to do? And you don't want the threads that simply spawn threads and say, you all do work while I sit and watch you. That's no fun at all. You want to make use of that really well. This is where async can take a couple of different options. One option is called deferred. Deferred means the thread that is calling the async is going to finish its work really quickly, and the asynchronous operation can actually run on the same exact thread. And it may be called by the thread that's calling it. A lazy and may run never also. This is even better. Hey, why do the work that shouldn't be done in the first place? So you can put it on a lazy mode, and then if I don't have a reason to ever run it, then don't bother running it. I can and just walk away. So you can do a deferred or you can do an async. Let's look at the difference of this. So notice in this example, I have a compute, and in this case, the compute position, and it's returning Fibonacci of the position, and I'm printing the thread ID in the compute. But on the other hand, in the main, I did async, but I called a deferred on it. Now notice the thread ID of the main. The thread ID of the main is 49916, but the thread ID of the compute is also 49916. And the reason the thread ID is the same is you said deferred, and the main said, gosh, I'm already done with my work. I'm going to block and wait on the result. When I'm blocking on it, I might as well do some more work rather than wasting this thread. And this is something extremely important because you don't want threads to block and wait and do nothing. That's a wasted resource. When a thread is blocked and doesn't do anything, you want to use the thread to do more work, and this knows to really do that, and that's exactly what you saw here when you said deferred. On the other hand, the same example I'm running with async rather than deferred. Now notice the thread IDs are not the same at all because the main is blocked on get. This one started on a different thread altogether. So you get to decide whether to use a deferred or to use async. There's no really one good answer. It depends on the problem you're solving. Sometimes you do want a fresh thread to be running it. Other times you don't mind this thread to really pick it up and run. You can pick and choose what may make sense. Well, okay, so that's great so far, but we come to the same problem again. Now you have a future, and you are saying, I know I shouldn't use a global variable. I know if I create a global variable, I have to use a mutex. It gets really messy. But I have a future. Now can I share the future? Now, that is no future at all, right? Because you're back to the same problem. Your contention is over the future now, and that's not going to be fun. If you ever want to share a future, there are two answers to it. First is don't. That's not a smart way of programming. And the second is if you do really want to do it, make sure you move the future between those calls by using using a shared future. So you want to create a shared future, and a shared future is thread safe. A non-shared future, a regular future, is not thread safe. If you call get on the future twice from multiple threads, your code will actually fail. Never share a future. If you want to really share a future, use what's called a shared future for that purpose, never a future itself. Well, okay, so we avoided this problem. We can pass data across. That's really nice. But what if we really want to implement serious algorithms with this? This is where what's called a packed task comes in. A packed task gives you a way to really create tasks in a way that when you call a packed task, it'll fire off a request on one side and give you a future on the other side. So it's a nice abstraction around this code to really create an async. So here's an example of a packaged task. So I say package task compute. This compute method will run on it when you start this package task, but you readily get a future out of it. So you don't have to do a hodgepodge of, I'll create a task over here, I'll get the future over here. You don't have to be brittle about this two endpoints. You can just package them. Hey, that's why they call it packaged. You can package them together and say, you go do this work, but give me a future on my hand. You're able to get the future right from it. So package tasks really make programming much more easier and pleasant. Keep in mind, when you use a package task, you are building on the future we just talked about. So what does this really look like? When you do this, on one side, it fires off an asynchronous request on a worker thread. On the caller side, it immediately gives you a future. So this is kind of like when you do this, it goes ping like this, and this code executes on this thread, and you are left with a future on your hand. So that becomes a nice programming abstraction. So don't use future directly unless you're doing some low-level stuff. Instead, use a packaged task. Now, like I said earlier, every time we solve a problem, it gives birth to a new problem. You say, okay, this is great. I don't want shared mutability. I want to use future. But what if something were to go wrong? If you call a method, it runs, it doesn't give you a result. Instead, it failed miserably with an exception. What gives? How do I get that exception on my side in a very civil way? That is the purpose of a promise. So a promise is a future which can handle exceptions. So when you create a promise may give you a result, or it promises to give you an exception. So think of a promise as a future which may either result in a success or may result in a failure. And that is exactly what this is doing. But the programming becomes a lot easier. Notice I have a promise on my hand, and I say promise.setValue when everything is good, or promise.set exception when something really went wrong, and this exception or the result will go back to the caller side properly. So if your code doesn't have any exceptions at all in it, if it's purely number crunching, you don't expect anything to go wrong in it, like division by 0, for example, choose a future, that's perfectly fine. If you expect something to really go wrong and you want to handle exceptions, then use a promise instead of using a future. That's a lot better. So how do we use this on this side? Well, notice I say result promise, and I say result promise.get future, and then of course that's going to give me the result. But if something were to go wrong, it's going to blow up on your side. So get future will either give you a result, or get future will throw an exception at you, and you can handle it on this side and you can deal with it. So that's all I have. Hope that was useful. Thank you.